These are solutions to Melham's Calc 3, Exam 3 for the 11 o'clock class. Number one, you just have to make sure that x is not equal to y squared. So I graph x equals y squared, which is a parabola open to the right, make it dotted and shading the rest of the xy plane. So it's the xy plane except for points that are on the parabola x equals y squared. Number two, if I come along the path of x equals 0, I have limit as xy approaches 0, 0 of 0 divided by y squared, which is 0. If I come along y equals 0, I get limit xy approaches 0, 0 of 2x squared divided by x squared plus nothing, which comes out to be 2. So I have two different paths with two different limits, therefore the limit does not exist. Number three, fx is 16x cubed y squared minus 9x squared y to the fifth. Fy is 8x to the fourth y minus 15x cubed y to the fourth. That means fxx is 48x squared y squared minus 18x y to the fifth. Fyy is 8x to the fourth minus 60x cubed y cubed. And fxy, which is the same as fyx, 32x cubed y minus 45x squared y to the fourth. Number four, z sub x is negative 2x, z sub y is 2y. Plug in negative 5, 4, negative 9. Z sub x is 10, z sub y is 8. Plug in z plus 9 equals 10, x plus 5 plus 8 times y minus 4. I would accept it if you stop there. You can keep going and possibly mess up like I did. 10x plus 8y minus z is equal to negative 9. Number five, dw dt is the partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt plus the partial of w with respect to z times dz dt. So that's negative y over x squared e to the y over x times 2t plus z over x e to the y over x times negative 1 plus e to the y over z times 3. 6 dy dx is simply negative fx over fy, which is the opposite of negative 2x plus 6y over 6x plus 3y squared. That's all there is to it. Number seven, unit vector is negative 4, 3 over the square root of negative 4 squared plus 3 squared, which is 5. So negative 4/5 comma 3/5. Gradient vector del f is 2 radical y, 2x times 1/2 y to the negative half, or 2 radical y, x over radical y. Plug in 3, 4. Del f is 4 comma 3 over 2. So I take the dot product for the direction of derivative. The derivative of f in the direction of u is del f dot u, 4 comma 3 halves dot negative 4/5 3/5. Negative 16 over 5 plus 9 over 10 comes out to be negative 23 over 10. Number 8, f of x, y, z is z plus y, x and negative 1. The gradient vector grad f or del f is negative y over x squared, 1 over x, 1. At the point 4, 2, negative 1, that should be a colon there, sorry. Negative 2/16, 1/4, 1, or negative 1/8, 1/4, 1. The maximum rate of change is the magnitude of the gradient vector. So radical negative 1/8 squared plus 1/4 squared plus 1 squared comes out to be radical 69 over 8. And the direction should be the direction of the gradient vector, negative 1/8, 1/4, 1, which I would accept. But if you want to make it nice with all integers, I multiplied by 8. So that gives me negative 1 to 8. Number 9, fx is 2y plus 2x plus y squared. Fy is 2y plus 2xy. Factors into 2y times 1 plus x. Fxx is 2. Fyy is 2 plus 2x. Fxy is 2y. The big D is 2 times 2 plus 2x minus 4y squared. So I set Fy equal to 0. That means y equals 0 or x equals negative 1. If y equals 0, then go back over here. If y is 0, that means x has to be 0. So I'm at the origin, critical point, 0, 0. If x is equal to negative 1, put negative 1 here, that means y squared minus 2 is 0, or y squared is 2, or y is plus or minus radical 2. D of 0, 0, put a 0 there and a 0, 0 there. I get 4, which is greater than 0. Fx is 2, so by rule we have a minimum. And f of 0, 0 comes out to be 4, and that's a minimum. D at negative 1 plus or minus radical 2, you get 0 minus 4 times 2, which is less than 0, you have a saddle point. So f of negative 1 plus or minus radical 2, if you plug into the original equation, you get 1 plus 2 minus 2 plus 4, that's 5, saddle point. Final answer, f of 0, 0 is 4, which is a minimum. F of negative 1 plus or minus radical 2 is 5, that's a saddle point. 10, del f equals lambda del g, using Lagrange multipliers. Del f is yz, xz, xy equals lambda del G, 4x, 2y, 6z. So yz equals 4x lambda, xz equals 2y lambda, xy is 6z lambda. The trick is to multiply this both sides by x, by y, and by z. That makes them all equal to x, y, z. Therefore, they're all equal to each other. 4x squared lambda equals 2y squared lambda equals 6z squared lambda. So lambda could equal 0, or if lambda is not 0, then that means 4x squared equals 2y squared equals 6z squared, or 2x squared equals y squared equals z squared. Now, if lambda equals 0, from here, lambda equals 0 means one of x, y, or z is 0. One of them has to be 0, which means f of x, y, z is equal to 0. One of them's got to be 0. Okay, and it either need to be the max or the min, because we're going to have a positive and a negative. So if lambda is not equal to 0, that means we have 2x squared equals y squared equals 3z squared, okay, which means this is also y squared. This is also y squared. So I have y squared plus y squared plus y squared equals 6. 3y squared is 6. Y squared is 2. Y is plus or minus radical 2. X squared is y squared divided by 2. Y squared is 2. 2 divided by 2 is 1. So x is plus or minus 1. Z squared is y squared divided by 3, which is 2/3. So z is plus or minus 2/3. So x is plus or minus 1. Y is plus or minus radical 2. Z is plus or minus radical 3. How do I maximize x, y, z? Well, the maximum is f of 1 radical 2 2/3. That means they're all positive, which is 2 over radical 3, or any combination of 2 negatives and 1 positive. To minimize, I make them all negative, f of negative 1, negative radical 2, negative radical 2/3, which is negative 2 over radical 3, or any combo where 2 positives and 1 negative from this list. All right, so that is Milham's 11 o'clock class, exam 3 for Calc 3.